Welcome back. In this particular lecture, we will talk about two-stage compression with water intercooler, liquid subcooler, and flash intercooler. Okay, so let's look at the schematic and the corresponding pH diagram for it. Okay, so now in this particular schematic, what we see here is give me a second. Yeah. Okay. So now what we have here is the evaporator. So in the evaporator, after the evaporator, the refrigerant enters into the low pressure compressor. So in the low pressure compressor, it is compressed to state point number 2. And the refrigerant goes to the water intercooler where it is desuperheated. So you can, so this is point number 3 where it is desuperheated, but not to the dry saturated state as we have mentioned previously also. Okay, so if you look at it, so here you have point number 3. So it is on the superheated state. So 1, 2, that is your isentropic compression in the low pressure compressor. 2, 3 is intercooling in the water intercooler, where it is not superheated to the dry saturated state. It is still in the superheated state. Okay, and then it enters into the flash intercooler over here. So when it enters into the flash intercooler, okay, what happens is the it is further desuperheated, and there it attains the saturated state. The vapor that leaves to the high pressure compressor from the flash chamber. Okay, so in this case, this is a dry saturated state. So if you look at this, so from 3 to 4, so from 3, it is in the superheated region. Then when it goes to the flash chamber, there it is converted into the dry saturated state. And then it enters into the high pressure compressor where it is compressed further to 4, 5. Okay. And then it leaves the high pressure compressor and enters into the condenser where it is condensed back to the saturated liquid state. So that is your point number 6 over here. So that is a horizontal line. And then you have a liquid subcooler where it is further subcooled to point number 7. So this is number 7. This is number 6. And then it enters into the expansion valve over here. So from the liquid subcooler, it enters into the first expansion valve, which is E1 over here. And there you have an expansion process of 7, 8. Before it enters into the evaporator, it goes to the flash chamber to make sure that it is in the saturated liquid state. So that is your point number 9. And then from 9, it enters into the second expansion valve where it is expanded further to the evaporator pressure level. So that is point number 10. And then in the evaporator, again, there is a heat extraction process where you have uh, the heat extraction that is taking place. So that is 10.1. Okay. So if you look at here, so from 7 to 8, I have mentioned that from 8, you are going to 9 in the flash chamber, and that part of the refrigerant is taken back to the evaporator. But there is also another branch over here. So let me show that with another color. So there is another branch that leaves 8 and goes to 4. So this is 8 and this is my 4. Okay, so what is point number 8? So at the end of the expansion, it enters into the flash chamber. So from the flash chamber, you have one circuit that goes to the evaporator through the second expansion valve. And there is another exit that goes to the high pressure compressor, which is point number 4. Okay, so that is something which you should keep in your mind. Okay, so this is there is supposed to be we can make an energy balance here and see that how this particular mass flow rate is taken into account. So here there are two subdivisions. So there is one mass flow rate. So let me mention it over here. There is one mass flow rate M1, which is the mass of the refrigerant that passes through the evaporator. So that is your M1. So M1 passes through the evaporator. What about M2? M2 is mass of the refrigerant that passes through the condenser. So in this circuit, the mass flow rate is M1, and in this circuit, the mass flow rate is M2. Either if you say mass flow rate, it's going to be M dot. If it is mass, it is simply M1 and M2. Okay, so when it comes to point number 8, so there is a branch that goes to 9 and there is another branch that goes to 4. Okay, so that is what happens when you use a flash chamber or a flash intercooler. Okay, so if you try to write an energy balance, so um, I didn't leave a space, so let me write it over here. So you have so let's say this is the flash chamber or flash intercooler. So there is an incoming from expansion valve E1, and there is another inlet that is coming from uh, the water intercooler. Okay, so these are the two entries. And then what you have is there is one exit that goes to the second expansion valve, and there is another exit that goes to the high pressure compressor. Okay, so this guy over here is M1, and this guy over here is M1. This guy over here is M2, and this guy over here is M2. So when it leaves to the high pressure compressor. So if you look at the layout, so it is leaving at 4, okay? And it is entering at 3. So this guy, the enthalpy over here is H4, and here it is H3. Okay, and for the expansion valve, I think it should be H9. Okay, so here the entry is 8 and the exit is 9. So H8 and H9. So the enthalpy here is H8 and the enthalpy here is H9. Okay, so now if you write an energy balance for this flash intercooler, so at the entry, so you have two entries which are marked with the red arrowheads. So M1H3 plus M2H8, that is equal to M2H4 plus M1H9. So if I have M1 on one side, M1H3 minus H9 is equal to M2 times H4 minus H8. So my M2 would be M1 times H3 minus H9 divided by H4 minus H8. Okay, so this is a simple energy balance which can be made at the flash intercooler because you have two entries and two exits at this common component, which is the flash intercooler. Okay, so this would be helpful in solving the problem. Okay, so now let's look at the problem and see a sample example, and let's see how we are able to solve this. Okay, so now in this particular problem, they have said in a 15-ton of refrigeration ammonia plant, compression is carried out in two stages with water and flash intercooling and water subcooling. The particulars of the plant are as follows. Condenser pressure is given as 12 bar, evaporator pressure is 3, flash intercooler pressure is 6. The limiting pressure, now they have said it is 20 degrees centigrade. Okay. Estimate COP of the plant, power required for each compressor, and swept volume for each compressor if the volumetric efficiency of the compressor is 80%. So they have given you the volumetric efficiency, which is 80%, and they want us to find the swept volume for each compressor. Okay. So they want us to find V1, and they also want us to find V3. So 1, 2 is the isentropic compression, and I think it should be 4, 5, isn't it? 3, 4 is, yeah, it's 4, 5. So it is supposed to be V4. Okay, 4, 5. So V4 would be the volume at the entry. Okay, so the swept volume of the compressor, that is supposed to be V4. Capital V1 is for the low pressure compressor, capital V4 for the high pressure compressor. Okay, so we are going to follow the same methodology which we did in the previous video lecture as well. So let's mark the state points in the pH chart. Once again, it is the ammonia refrigeration system. So here they have said it is 3 bar. So here you have the 3 bar pressure line. So this is going to be my evaporator pressure. And the mid pressure, I think it's 6 bar, isn't it? Yeah, it is 6 and 12. And the limiting temperature is 20 now. So this guy is my intermediate intercooler pressure. And let's say this is going to be my 12 bar, which is my condenser pressure. So this is 12 bar over here. So 3, 6, and 12. Okay, so I fix point number 1 on the saturated vapor line. So this is my point number 1. Just like in the previous case, let's use brown over here. So this is my point number 1. So we are supposed to follow the constant entropy line, and luckily it is on S equal to 5.75. So we have to travel across it till you reach the 6 bar intermediate pressure line. So this is my 6 bar intermediate pressure line. So let me travel across. I think this is my 6 bar over here. So this is my point number 2. Okay, according to the statement of the problem, I had to go to the 20-degree line. So this is my 20-degree centigrade line. So that is my water intercooling. So that is my point number 3. So that is on the 20-degree centigrade line. I should draw a horizontal line from 2 till it reaches the 20-degree line. So that is my point number 3. So now I have to once again take the constant entropy line till I reach the 12 bar. So in my case, this is my 12 bar over here. So let's say uh, it's it's at this particular point. So this is my point. Oh, sorry, we forgot something. Okay, sorry about that. How about point number 4? We all, after the water intercooler, we also have the flash intercooler. So we are supposed to reach the saturated vapor line over here. So this is going to be my point number 4. I forgot that. So when you have water intercooler, that is 2, 3. Then you also have the flash intercooler, so that is 3, 4. And then you have to travel across the constant entropy line, and that comes here to here. So this is my point number 5. Okay, so on the 12 bar pressure line, so I think it is supposed to be a horizontal line. So point number 5 is a little bit lower. So let's say, so this is my point number 5. Then on the condenser, I reach the saturated liquid line, which is point number 6. And then I also have the liquid subcooler, which is the 20 degrees centigrade line. So as I have shown you, so this is the 20 degrees centigrade line. So I should go up to this. So this is going to be my point number 7. So from 7, I'm going to the intermediate pressure line. So that is point 8 here. And then I have to go to the saturated liquid line. That is my point number 9. Then from there, drop a vertical till you reach the 3 bar. So that is my point number 10. From here, draw a horizontal till you reach the saturated vapor line. Okay. And don't forget to join 8-4 also. Okay. So since I am using the tablet, so I'm not getting the exact value. So I have just shown you the procedures. So I want you to do this and check it and see if the values that you're getting are coherent with what I am getting over here. Okay. So now let's look at the enthalpy values. So just like the previous case, this is my H1. H1 is somewhere between 1400 and 1500. So it seems to be in between the midpoint. So it's in the midpoint. So let's say 1450. I have already said that the unit for the enthalpies are kilojoule per kilogram. Okay. And point number 2, that is a bit closer to 1500, or it is also somewhere in between, but closer to 1600. So let me say it is 1560. And H3 is on the 1500 line. So H3 is 1500 kilojoule per kilogram. And H4 is a little bit away from H1. So let's say 1470. Okay. And then H5, it is closer to H3. So midway between H2 and H3. So let's say 1530. And then you have H6, which is between this line and this line, exactly midway between this line and this line. So that is 300 and 400, let's say 350. H7, so that is very closer to the 300 line, let's say 290. And which is also equal to H8. Let's say H9. H9 is midway between this guy and this guy, and a little bit inclined towards 200, let's say 230. Okay, so these are the values that we have got. Okay, so to identify the COP value, it's going to be easy. It's the same methodology. So you have the refrigeration effect. Refrigeration effect is going to be H1 minus H10 or H9. So H1 is 1450. and H10 is 230, which is also equal to H9. So H9 is 230, which is also equal to H10. So that leaves you with 1220 kilojoule per kilogram. Okay. And then you have work input for the low pressure compressor, which happens to be H2 minus H1. And H2 is 1560 minus 1450. So that is 110 kilojoule per kilogram. And if you look at WHPC, so that guy is H5 minus H4. So H5 is 1530 and H4 is 1470. That is 60 kilojoule per kilogram. So W net would be WLPC plus WHPC, and that happens to be 170 kilojoule per kilogram. Okay. But what they have also given is the refrigeration effect has given us 15 ton of refrigeration. Okay. So they have also said 15 ton of refrigeration. So RE is also 15 ton of refrigeration, 15 into 3.5. How much is that? So let's check with calculator. 15 into 3.5, that is 52.5. This guy is 52.5 kilojoule per second. Okay, so if I want to find the mass flow rate, so this refrigeration effect, that is M1 times H1 minus H10. Okay, so M1, let me erase this over here. So M1 or M1 dot is so I'm talking about the refrigeration effect. So it would be 52.5 divided by 1220. So that would give me 52.5 divided by 1220 is 0.043. So 0.043 kilogram per second. And you can write the energy balance just like we wrote in the previous slide. So M2 is this guy. Okay. So M1 dot, we found that as 0.043 over here, and H3 minus H9, 1500 minus 230, 1500 minus 230. So 1500 minus 230 divided by H4 is 1470 minus H8. H8 is 290. So this guy is 290 over here. So there is a small correction we have to do with WLPC and HPC because the mass flow rates are different. So 1500 minus 230 multiplied by 0.043 divided by 1470 minus 290, which is 0.046 kilogram per second. Okay, so now the correction that we have to make is for the high pressure compressor, I have to multiply it with M.2. And for the low pressure compressor, I have to multiply it with M.1. So this guy should be multiplied by 0.043, and this guy should be multiplied by 0.046. So multiplied by 0.46. Okay, so let's see how much you are getting. So 1560 minus 1450, that's 110, isn't it? Multiplied by 0.043, that's 4.73. So this is 4.73 kilowatts. And 1530 minus 1470 multiplied by 0.046, that is 2.76. So if we erase this, we would be getting 4.73 plus 2.76. 9, 14, and 7.49 kilowatt. That is my W net. Okay, so 52.5 is the refrigeration effect and 7.49 is the work input. So it's a pretty good refrigeration system then. So COP is refrigeration effect divided by work input. So it's 52.5 divided by 7.49, which is 7.5. So let's see, 52.5 divided by 7.49. So that's 7. So the COP is 7, the number 7. Okay, so that is the COP. So we have estimated the work input to both the compressors and we have also estimated the COP. But they also want us to find the swept volume of both the compressors. Okay, so now we need to find one more input over here. Okay, so if you look at point number one, I have marked over here. Okay, and if you look at this green colored lines that are passing through, V is 0.40, which is in meter cube per kilogram, the specific volume. So if you look at the green color line that passes through 1, that is 0.40. So which means, let me write it on the next slide. So let me write it over here. So V1 is 0.40 meter cube per kilogram. Similarly, input at 0.43. So the green color line that passes over here, that is V equal to 0.20. 0.20 line, no. Which line passes over here? The line that passes over here is V equal to 0.25. So V4 is 0.25 meter cube per kilogram. Okay, so if you multiply it, so if I want to find the actual volume that is taken in is M1 dot into V1, which is 0.043 multiplied by V1 is 0.4. And capital V4 would be M2 dot into small v4, because M2 dot is the mass that is entering into the high pressure compressor. Okay, so if you want to find out these two values, so it's 0.4 into 0.043, that is 0.0172. 0.0172 meter cube per second. So 0.25 into 0.046, that is 0.0115 meter cube per second. And the volumetric efficiency is given as 80%. Okay, so volumetric efficiency is actual intake by swept volume. Okay, so if I want to find the swept volume for the low pressure compressor, let me denote it with VS1. So that is capital V1 dot divided by volumetric efficiency. So that is 0.0172 divided by zero point 0.8. Similarly, VS4 would be V4 dot divided by volumetric efficiency. V4 dot is 0.0115 divided by zero point 0.8. Okay, so now let's see what we get out of this. So 0.0115 divided by zero point 0.8 divided by zero point 0.8, that is 0.0144. 0.0144 meter cube per second. So that is the swept volume. And this is supposed to be greater than this. Okay, and that's how we get it. That's fine. 0.0172 divided by zero point 0.8. So that is 0.0215. So that is the swept volume of the low pressure compressor. And this is the swept volume of high pressure compressor. Okay, so thank you.